Alright, g'day, welcome to lecture 1.3 of Unit 2, Nuclear Equations. Here are the learning intentions and success criteria for this chapter. Please pause the video and attempt to complete the knowledge and skills table. Okay, so hopefully as you're going through here you recognise that you need to know, well, firstly, what is a nuclear equation? Don't know that, it's pretty hard to do a lot of these things here. We want to know, well, what are nucleons? We did cover that in a previous video, so if you need a better definition, go back to check one of those. I believe it was video 1. We want to look at what are the causes of radiation, so what's actually making this happen. We know the atom is unstable, but what type of instability is causing this? And finally, we need to definitely know what is a decay series. Now, most of this here are knowledge verbs, but there is this construct verb here, which is a skill. So you need to know how to do this actual thing. So you've got to construct the nuclear equation and balance the nuclear equation. Alright, so in our last video we looked at types of radiation and we have these four. So these are the four symbols I will be using to represent each of these. These are the standards prescribed by our syllabus. Alpha radiation, remember, is a 4-2 plus 2 helium particle. Beta negative is an electron with a negative 1 down here. You might go, well, why has this got the plus 2 up here and this has got the negative 1 down the lower front? This is to make the equations a lot easier to balance. Realistically, we could say that this is going to be 0, 0, minus 1 up there, but it makes it a little bit trickier to deal with some of the math, or at least it makes it that you've got to remember more to do some of the math. We've got a beta positive, and we have gamma radiation. Sometimes you'll hear me call beta positive positron radiation, as that is the other name for a beta positive particle, a positron. Okay, so let's look at alpha radiation. So an alpha decay occurs when an isotope is too large for the strong nuclear force to overcome the entire electromagnetic repulsion. Now remember that in an atom, the adjacent nucleons, the protons and neutrons, they're attracted by the strong force. Okay? So they're attracted to each other. But all the protons repel each other. So here we have, well, here's a neutron and a proton, they're attracted to each other. These two protons would have some attraction, these two neutrons would have some attraction, but it's only ever two next door. This proton and proton, they're not next door to each other, but they're pushing away. They'll also be pushing away, they'll be pushing away, they'll be pushing away, they'll be pushing away, they'll be pushing away, that'll be pushing away. Every single proton you can see there will have repulsion on every other single proton, while the nucleons will only be attracted to the ones right next door. Okay? So because it removes an entire alpha particle, it should become more stable. Okay? Spits out a bit. The result could end up doing more, so plutonium into uranium-236 here is probably going to still be pretty unstable because it's quite big, and so then it would have another decay. But this is more stable than this. It just might not be entirely stable. So let's have a look at some examples. I've got here two examples of uranium-238. Sorry, two examples here, one uranium-238 and one is platinum-175. So the way I like to do these is to straight away go, well, I've got uranium-238, I've been told it does alpha radiation, let's write an alpha particle first, He2+, and then work out what's left over. Now, the way I do this, and the easiest way to do it, is to just make sure that these numbers here add up over the whole thing. So, don't worry about the charge, that's just to say that it's positive. 238 take away 4 gives me 234. 92 take away 2 gives me 90. Now, the reason I've got the periodic table down here, and this is just a cutout from the one you will be provided with on exams. I'm now looking for element 90. I can see element 90 is thorium, it's 2 down from uranium, so TH, and we're done. Okay, that's simple. Now, in this case, I know uranium-238 is also called a gamma emitter, and so I would then slap a gamma particle on the end. Now, this one is the one example about alpha radiation from your syllabus. Okay, so this one I would expect you to memorize that it is uranium-238 is definitely a gamma emitter. Any other ones that are gamma emitters, you'd be told that they're a gamma emitter. Okay, so if you aren't aware of it, you're not sure, don't put it on. Like, I don't know if this platinum 175 is a gamma emitter, so I'm not going to put one on there. Let's do the same thing for platinum. 42 He2 plus platinum, so 175 take away 4 gives me 171. 78 take away 2 gives me 76. And element number 76 is platinum, down 2 is osmium. Okay, but I don't know if I don't know if that platinum isotope emits gamma radiation, or if I don't know that osmium isotope is unstable and emits gamma radiation. So we're not going to put one on there because I don't know. As I said, an exam question should tell you if it is a gamma emitter, because there's no indication that you need to memorize that they're gamma emitters. There is some stuff with binding energy that we will talk about down the track in a couple of videos from now that may let us indicate if it is, because if the actual masses, if we know the actual isotope mass of thorium-234 and helium-4 as the alpha particle and uranium-238, and the actual masses don't add up, that leftover mass will be our gamma particle there at the end. Same thing for here, but for now we don't have any indication for that. So let's go on to beta negative. The result of a beta negative emission is that a neutron becomes a proton. Now the actual mechanism of that will be talked about in topic 3 when we look at the standard model in this unit. So what we need to know at this point is that beta negative emission occurs when the ratio of neutrons to protons is too far towards the neutrons. And as such, if I turn one neutron into a proton, it would become more stable. So here we've got beta minus decay, so here we've got a proton and 2 neutrons, right? And here we've got 2 protons and 1 neutron. So this neutron here at the top has become a new proton. So here we have, that's 3, so that would be hydrogen 3, and there's 2, so that'd be helium, so this has become helium 3. So this one has converted to this, and there's an electron on the end. That's our beta negative particle, it goes very fast. Right? There is also an extra particle called an anti-neutrino for beta negative. Okay, you've got to memorize that. It's a type of antimatter. This is why it's called an anti-neutrino. And the symbol we give it is the Greek letter nu. It's kind of like a curvy V with a little hat on top. Now, the syllabus uses a triangle hat. The textbook that we're using gives a straight line hat. My personal preference, and this is what I was taught at university, was to use a squiggly hat. From what I can tell, it doesn't matter what you use, just so long as you indicate that it is an antiparticle. Right, so here's a random text I found with an example I'm about to do, cobalt-60. We can see the count there, it becomes nickel-60. We can see that these two still add up to 60. Here's our beta particle, our electron, and here's our anti-neutrino, the V, or the Greek letter nu, I should say, with the hat on top. Okay? Let's have a look at some examples. So first off, we have cobalt-60 here. I'm going to do it the exact same way I did with alpha emitter. I'm just going to start off, I'm going to draw my beta particle. Okay, if I'm told that it's a beta negative emission, first thing I'm going to do is draw my beta negative. A lot of texts will have, just by convention, they will put the daughter isotope first, whatever the big chunk is. But there's no actual requirement to do that. So to me, I personally go, let's put this thing first so I can see the math directly here, and it makes it a lot easier for me to deal with. So 60 take away 0 is 60. That's pretty easy. This one's the tricky bit though. 27 take away -1 is 28. Remember, when you subtract a negative, it becomes the same as addition. If you mess that up, you'd be doing beta positive radiation, and you will not get the marks for it. Okay, so we know that it's 28. Let's find cobalt. 28 is the next one up, so that's nickel. And because it is beta negative, we need to add our neutrino and make it anti. So there we go, there's our neutrino with a squiggle. Now, this one I know also involves gamma radiation, so let's slap some gamma radiation on the end of it as well. Other ones you might not know if it's got, or you might know it definitely doesn't. The carbon down here doesn't involve gamma radiation from what I can tell, so we're not going to have that on there. This is one from your syllabus though, okay? I would probably recommend you recall, or definitely memorize, that cobalt-60 is also a gamma emitter, just in case. Okay, carbon 14, let's do the same thing. 0, minus 1, E. Okay. 14 take away 0, 14. 6 take away negative 1, 7. Carbon goes up to nitrogen, plus, and this one has an anti-neutrino, and this one doesn't have any gamma radiation from what I know, so we'll just leave it like that. Okay, so beta negative, pretty straightforward. You're looking either side of the particle. I don't really care about, I don't think it's worthwhile memorizing that, oh, with a beta negative it goes up by 1. To me, the math lets me remember, does it go up by 1? All I've got to make sure is that the 14, the numbers on the top, 14, 0 plus 14, at balance, 6, minus 1 and 7, balance. Okay? If you remember that, then it's easy to figure it out, and because you'll always have a periodic table with you when you are doing these in your exam. Remember, the other type of beta radiation is beta positive radiation. Now this is the opposite of a beta minus or a beta negative, and as such the radiation, remember, is the opposite too, and so is the rest of the nuclear equation. So this occurs when the number of protons is too high for the number of neutrons. So again, same sort of image down here. We can see that this proton here has now become a neutron. The total number of things is still the same, but the balance has changed from a 4 to 3 to a 3 to 4. There is also the anti-electron, the beta plus particle coming off here, and there'll be the neutrino in a second as well. And this is what allows it to become more stable. There is the extra particle, as I said, it's called a neutrino though, and the way I remember it is that when you have an antimatter electron, you've got a regular matter neutrino. When you've got a regular matter electron, like we saw with beta minus or beta negative radiation, it has an antimatter neutrino. Okay, they've always got to have the opposite for each other. And the symbol for the neutrino is just the mu, the nu symbol without the hat on top. Okay, so pretty straightforward there. Let's have a look at some examples. So here we have tin 102 and carbon 10. So tin 102, let's firstly start with symbol, plus 1, E. Okay, 102 take away 0 is 102, 50 take away 1 is 49, and so this becomes indium, plus neutrino. Now, I know this one is also a gamma emitter. This one is the one from the syllabus, so I'd recommend you memorize this one. So tin 102 is a gamma emitter, okay, and so that would be the full sequence. Carbon 10 though is not, as far as I can tell, a gamma emitter. So let's do this one. 10 take away 0 gives me 10. 6 take away 1 gives me 5. And element number 5 is boron, plus my neutrino because it's beta positive, and we're done. Okay? There are some, you can also get an example of beta positive radiation, or it looks the same as beta positive radiation in terms of the nuclear mutation it does, so nuclear transmutation it does. And that's called electron capture, where an electron, so if I was to do it like this, 10(6C) plus an electron, if the electron was to smash into it, well, this thing has a 0 and a -1 effectively. Well, 10 plus 0 is 10, 6 plus -1 is 5, would become boron. Okay, but there wouldn't be any emission coming out of it. This occurs because when this thing smashes into a proton in there, a proton plus a electron merges to become a neutron essentially. Okay. So you can get other forms of beta emission that may appear in your readings, or they may appear possibly as a teaching type moment on an exam. Realistically though, it doesn't matter what type of radiation they describe to you. If you consider it something that is being added to it, put it on the side before the arrow. If it's something that's coming out of it, put it on the side after the arrow, and just make sure that these numbers at the top and make sure these numbers at the bottom add up. If you do that, you're golden. Okay, so it's not a terribly difficult thing to work out nuclear transmutation equations, but you do have to be aware that they have to balance. Now the last thing is gamma radiation. So we've done a couple of examples, and here are two of them. In this case, this is directly from the syllabus. So you can see here we've got the big daughter isotope first, and then the alpha particle. While the way I did it, I drew the alpha particle first to make the math easier. This is kind of the conventional way of writing these things. There are no equations really that just have gamma emission, at least they aren't in our syllabus. And gamma ray will be the excess energy from the change in what we call the rest mass of the particles, and we will talk about that when we deal with binding energy in a couple of videos. If the question tells you that there's energy released, add the gamma symbol. Down the track you may have to work out if energy is released. There's nothing in the syllabus that indicates that, but it's not something that is something you would be able to do if you're instructed to do it, because we'll be learning about binding energy. The other way of representing this, though, is that sometimes they will do the alpha and beta decay on one line and then a separate line for the gamma equation, and they represent the need for this to happen with a star. There is an example of this in question 5.4, but I want to talk about it directly. So here we have, this is the same decays here. Uranium-238 becomes thorium-234, starred, plus alpha particle. Okay? Then the thorium-234 with the star becomes thorium plus the gamma ray. Because technically this gamma ray does come from this thorium nucleus after it's kicked out the helium. People just tend to combine the two together into one long step. Same thing here with the cobalt. Firstly, the cobalt becomes the nickel, starred, so it's energetic, kicks out the electron, kicks out the anti-neutrino, and you can see here's the hat symbol that, or with the little upside down arrow that the textbook is using, and that becomes energetic nickel, which then becomes calm down nickel plus a gamma photon that's being kicked out of it. So there are a couple of ways of doing gamma radiation. Sometimes they will be on a separate line with whatever text or whatever research you're doing. Sometimes it'll just all be on one line, and really it doesn't matter. It may be something that you could read into a little bit, or represent it two different ways to communicate your understanding. But ultimately, if you were to say that this is the decay equation for uranium, well, it is, because that's what it is in the text. The last thing I want to talk about in this is something called a decay series. So when an atom decays, doesn't spontaneously mean that the resultant is going to be stable. The product might not be stable. And as such, an atom can go through many decays before finally reaching stability. This decay series graph in our text is a really good example of how you can visually represent the decay series of an isotope, and it's something you could be asked to interpret on an exam. So we can see here, and I'd recommend getting your book because it's a bit small. Here we have uranium-238, and it's going down by alpha radiation to thorium, and then by beta radiation it goes across to uranium-234, and then it goes down by alpha radiation to another type of thorium, and then down by alpha to radon, then down by, radon I think, then down by alpha to another one. And so it's going down these series here. This is certainly something that you could be expected to explain. Like if I said, well, what's the third product from the decay of uranium-238? Well, product number 1, product number 2, product number 3. Sorry, we missed palladium there in the middle. So you can go, you can count along these things. Note that the betas only ever go left to right. They're going horizontally here. Here's an example of the beta plus one. I think that's why they've included that there, because uranium-238 doesn't go through any beta plus on this, while all the beta minuses are going to the right, and then the alphas are going down because of the graph, down diagonally. So this is something that you could read and interpret in order to talk about decay series or to write a decay equation. There's nothing saying use this graph to write the decay equations to go from uranium-238 to uranium-236. 234. That is certainly a very possible type of question. Okay. So, in this video we have done the following. We have identified the cause of different types of nuclear radiation. We've crafted nuclear equations and predicted their outcomes. And finally, we've discussed how radioisotopes can go through a decay series before they become stable. Before your entrance to class, you've got a few questions in this, sorry. I'd like you to complete questions 1 to 7 in chapter 5.3 and 1 to 7 in chapter 5.4 and copy those answers into the 2.1.3 space on eLearn. There aren't any subparts in these questions, so it will be about 14 questions, but they are all pretty much worthwhile to do. Alright, thanks for your time guys, and study hard.